Welcome everyone. Today we're going on a quick tour of PyTorch. It's one of the most popular deep learning frameworks out there. We're going to cover essentials such as tensors, data loading, model building, all the way to saving our trained parameters for later use. So what exactly is PyTorch? At its heart, it's a library designed for tensors and deep learning. Unlike some other frameworks, PyTorch is mainly famous for its dynamic graphs. So essentially, PyTorch has a very similar feel to Python, allowing it to be a little easier to understand math concepts and use more advanced functions. Um, Within PyTorch, we use torch.nn to instantiate neural networks or logistic regression. We'll also be training via AutoGrad and torch.optim. AutoGrad will calculate our math gradients. Torch.optim, short for optimizer, will update our weights. And then additionally, PyTorch is able to be run on GPUs and accelerators. So essentially the mental model that we want to keep in mind is that data becomes tensors. Tensors are fed into our model where they produce a loss error, essentially how off were they from their actual target. Then we calculate our gradients for each node in our neural network. Now, finally, our optimizer will update all of our values. Now let's talk a little bit about tensors. So there are essentially ways that we can represent matrices in Python. So if you've dabbled with NumPy uses arrays. PyTorch uses tensors, which can be run on GPUs. This is able to save space on the CPU for other computations. So their attributes are shape, which shows you the rows by the columns, the data type it utilizes, along with its device, whether it's running on a CPU or a GPU. So as you can see here, these are some examples of how to instantiate tensors. This will create a 2 by 2 tensor. It will be 1, 2, 3, 4. And then we can also make a ones tensor, which is all ones. It'll have 2 rows and 3 columns. Then we can even make a random tensor. So when we load data into our model, it can get very wonky. So PyTorch has a built-in function called dataset, and dataset allows us to create pairs between our training data and our target data. So you can either use PyTorch's built-in dataset, or you can make your own, as long as it implements these two functions. The length, you can be able to find the length quickly, and get an item for a specific item in the dataset. Additionally, we use a data loader to be able to load the data into our model. So this will create an iterable around these where our PyTorch, our Python loop, will be able to understand how to go about traversing our dataset. Data is very rarely ready for training out of the box. Transforms are functions that we use to manipulate our data and pre-process them. So initially we'll use toTensor to convert an image or an array into like a tensor that the GPU can understand. We'll also use lambda transforms for things like one-hot encoding, which I'll get to a little later. And then we can also use this within our data set definitions. That way we can be able to feed data into the model in a more efficient, understandable method. So now we'll go ahead and start building our model. So our first model that we want to build essentially would be a neural network, or it can be a linear regression, logistic regression. We're going to define it using the initiation function, which in this case would be model x. So we don't want to call forward x, we always want to call model x. That's one thing that we always want to keep in mind when instantiating our neural networks. Now, next we compute the gradients for every computational graph. So when we call our model x function, this is essentially going to go ahead and run all of our values through our machine learning model. It'll go through all of our neural network nodes and produce one final value. Now, in order to understand where a node went wrong, we need to be able to backtrack. That's where loss.backwards comes into play. So essentially what we'll do is we'll use the chain rule to be able to go backwards and calculate the gradient for every single node to be able to update our weights across the board. When we're testing, we want to make sure we use torch.nograd or detach. That way we are not calculating any gradients. We're essentially just calculating our loss errors. So this is a more in-depth slide of the previous slide. In order to minimize our loss error or our loss function, there is a three-step update. So we're using cross entropy loss because this would be logistic regression. What we'll do first is we're going to zero all of our gradients. We want to make sure that we start off with a clean slate. Any previous gradients have already been applied. We need to zero those out. Next, we're going to use loss.backwards to compute all of our gradients and essentially use the chain rule as I said previously. Then our optimizer is going to go ahead and update all of our weights. So when we do optimizer.step, it computes all the gradients along with the weights and produces new weights for us to use in our next iteration of the training model. Lastly, we want to be able to save our model and upload it into other programs. That way we're able to actually use our trained machine learning model in our standard. It could be Netflix, it could be other programs that we may be building. In order to do this, we're going to save only our weights using a state dictionary. Essentially, it's a dictionary, but the standard terms you call it state dictionary. Now what we'll do is it'll be saved. We'll use this function to save it into a certain file. Way later, we're able to load the dictionary into our new program later. Now, when we want to utilize our new model, we need to ensure that we switch to model.evaluate. That way, we're not training our model and ruining our new weights. We want to ensure that we're using model.eval. That way, we're actually producing values. We're not training the model again. Now, lastly, this is my sources. These are the different resources that I utilized for this presentation. I recommend checking them out, especially the PyTorch official documents. This is where I got all of my data from, especially this basics, the beginner basics tutorial series. Thank you for watching my slideshow. Now I'm going to go ahead and show you a tour of my actual program where we'll be able to see all of this in action. Alright, let's show a quick demo of my project and exactly how it works. So, actually we're going to import all of our important packages. This includes sklearn, torch, numpy, pandas, and matplotlib. Now we're going to start pre-processing our data. When we pre-process data, there's a series of steps we must take to ensure that there are no open-ended values, no room for error essentially. So we'll start by importing the raw data into our file. We're going to replace any missing data. So as you'll see later, how I deal with missing data. Categorical data as well. So essentially, categorical data refers to data that's not expressed as numbers, but more as different categories. So for example, color of a car might be white, red, orange, etc. So we need to make sure that everything can be expressed as an integer in order for our model to be able to recognize that value. We want to separate our data set into our data and our target, split into training, validation, and test data. And then essentially, since our data means are all over the place, our model might take way more time to understand how our algorithm works, how it should learn. So we're going to scale all of our data in order for it to be around a certain range where the model can work with it much better. We're going to convert all of our arrays into tensors, and then we'll finally create our data sets and data loaders. So let's start with our missing data. So when I went through our diabetes data, I saw that there were places where there are zeros where there should be non-zero values. For example, glucose, blood pressure, insulin. So this must mean that these values should have been nullified or nan. So in order to replace them using Panda's built-in fill and a function, we need to replace all those zeros with nan. So what I did here was I marked all the columns that could potentially have missing values. or zeros essentially. Then over here, we make a copy of our data. And then wherever our column that's missing that value, we will replace all the zeros with np.nan. Finally, within our for loop, we'll go ahead and replace all our nans with the mean of the data. So this is called imputing. So as you can see here, in places where there would have been zeros now contain the mean. So insulin, for example, these would have been zeros, but they've been replaced with the mean. Now let's go ahead and scroll down and take a look at our features and how we split it into training and validation data. So X is going to be our entire data set without our outcome column. So we're going to drop the outcome and instead we'll assign it to Y. Then we'll split into two groups. We're going to start by splitting into our training, validation, testing data, and then our Y training, Y validation data. So we'll split those first, and then we'll split them into testing. Then we're going to scale all of our inputs, as I said before. So we'll use a scaler. We're only going to fit our model to our training data. We don't want to fit it to our validation or test data, especially the test data. This is important. It should not be able to look at this data yet. Then we're going to convert everything to tensors in order to be able to utilize PyTorch's functions. And then lastly, let's take a look at what xtrain looks like afterwards. So you can see these are all scaled to around a similar value in order for our model to be able to recognize them much better. Now, we're going to create data sets and we're going to use data loader to load them. So tensor dataset is going to create XY pairs. Essentially, we're going to take this first column right here in our training data, and we're going to match it to the first column in our Y data. Then data loader is going to go ahead and create batches in order to feed them to our model a little bit at a time. That way it doesn't end up memorizing the data, it ends up learning from it, and we can track its progress this way. And we'll also shuffle around certain data labels and numbers in order for our model to start understanding where numbers are coming from and understand how to go forward. So we'll save this. So now if we take a look at all of our data, our xtrain.shape is going to be 460 by 8. Same thing, our ytrain is going to be 460 by 1. So these should match up perfectly. Our validation data is 154 and our testing data is 154. So this creates a 60-20-20 split. Now we'll go into our training loop. So our training loop works like this. We're going to first set our model to train. Then we're going to go through our train loader. And for every XY pair, we're going to create predictions, log our loss function, and then we're going to use optimizer.zeroGrad to clear all of our gradients. Loss.backwards, we'll use the chain rule and go backwards through our neural network in order to calculate all of our gradients. Then optimizer.step updates all of our weights. Now to keep track of our training loss, we're going to add it to our train loss 0.0. And then over here, we'll divide by the length of our train loader. So that will give us what our average train loss was, our average training loss was throughout our program. Then instead of having model.train to be true, now we're going to evaluate our model. So over here, it's a similar program to the one above. However, this time it's more trying to test the model using our validation data. So I'll run some code down below and we'll be able to see this in action. So over here, I create our learning rate, our logistic model. We set our optimizer to be SGD. Then our loss function is going to be the sigmoid function along with the cross entropy function. And then we'll do 30 epochs at a time. So if I was to run this, we're going to see a bunch of different outputs. So each time it's doing about 32 values. So as we can see here, our training loss does go down, which is good. Starts at 78%, we end up around 48%. And then our validation accuracy also goes up pretty high. It starts at 45%, we end around 72% accuracy. So now let's test our data. So from our test loader, we're going to go ahead and test all of these and get probabilities. And then we'll take a look at what our ROC-AUC was. So in this case, it was 85%, meaning that there's an 85% chance it's going to be able to determine correctly whether you have diabetes or not. Now, when it comes to this data, from a human standpoint, you would want more false positives than false negatives, because the false positive might prompt further testing of the patient. However, false negative would prompt less testing, meaning that there's a higher chance somebody will walk away with diabetes and not know about it and cause issues later on in life. So, our model, if it cannot determine properly whether a person has diabetes, it'll most likely fall upon the false positive, which is why you see this little increase over here, because at first it's able to calculate the true positive pretty well, and then at times where it doesn't understand whether something is false or true, it'll auto default to false positive. That way we can be on a safer side and fully understand whether this person has diabetes or not. As if they don't have diabetes and the model doesn't know and it produces a false positive, we can do more testing and later we'll see that there actually is no diabetes. And this is my program. I hope you guys enjoyed.